In the first days of July 2022, the James Webb Space Telescope opened its eyes. Not metaphorically, literally. The first scientific images were released on July 12, 2022, and within those first days of operation, the telescope's instruments began returning data that troubled astrophysicists. Not surprised them, not delighted them, troubled them. Because what Webb saw did not fit what was supposed to be there. Galaxies, massive, mature, structured, containing hundreds of billions of stars, appeared in such an early period of the universe that they simply should not have had time to form. The stars should not have had time to assemble such structures. The chemistry should not have had time to enrich the interstellar medium to such a degree. But there they were, and they were calling into question models that astrophysicists had spent decades building. Not small questions, large ones, fundamental ones. Tonight we are going to walk through this story honestly. Not through headlines, through the physics, through what Webb actually found, why it matters, and what it tells us about the universe we live in. If the night is long, stay. Let us begin with the most basic thing, with what the James Webb Space Telescope is and why it sees what Hubble could not. The James Webb Space Telescope, JWST, is the largest space telescope in history. Its mirror has a diameter of 6.5 meters compared to the 2.4 meter mirror of the Hubble Space Telescope. The collecting area is 6.25 times larger. This means Webb gathers 6.25 times more light than Hubble in the same observation time. But the key difference between Webb and Hubble is not the mirror size. The key difference is wavelength range. Hubble operates primarily in the visible and ultraviolet range. This is why its images are so colorful and vivid. Visible light is exactly the range our eyes perceive. Webb operates primarily in the infrared range. This is thermal radiation, long wavelength, invisible to the naked eye. Why does this matter fundamentally? Because the universe is expanding, and when the universe expands, light traveling through it undergoes redshift. Redshift is the stretching of a light wave's wavelength as space between the source and the observer expands. Light that left a source as ultraviolet or visible after billions of years of travel through an expanding universe arrives at us having shifted into the infrared. The most distant objects in the universe, those that existed in the first hundreds of millions of years after the Big Bang, have such high redshift that their light has completely shifted from the visible into the infrared range. Hubble barely sees this light. Webb sees precisely it. This means Webb looks further back in time than any previous telescope. Not slightly further, fundamentally further, to epochs that were practically inaccessible before. Let us now talk about how observing distant galaxies actually works, about what it means to see an object billions of light years away. When we look at a distant galaxy, we do not see it as it is now. We see it as it was when the light we are currently receiving left it. Light moves at 299,792 kilometers per second. This is fast, but finite. Light from the Sun reaches Earth in about 8 minutes. Light from the nearest star, Proxima Centauri, in 4.24 years. Light from the Andromeda Galaxy in 2.537 million years. A telescope is a time machine. The further the object, the deeper into the past we look. The universe began 13.8 billion years ago. This is called the Big Bang. The first stars formed approximately 100 to 300 million years after the Big Bang. The first galaxies around the same time or slightly later. When we observe a galaxy at redshift Z equals 10, we see it as it was approximately 500 million years after the Big Bang. This is a young universe, very young. Hubble reached redshifts of about Z equals 10 to 11. This was already the limit of its capabilities. The most distant objects discovered by Hubble were at the edge of what was accessible. Webb reaches redshifts of Z equals 13, Z equals 14, Z equals 16 and higher. These are objects that existed 200 to 300 million years after the Big Bang, practically immediately after the first stars. No telescope has ever looked this far back. Let us now talk about the specific discoveries that created the problem, about what Webb actually saw and why it should not have been there. In the first months of Webb's operation, even before results were peer-reviewed and published in journals, scientists began noticing something troubling in preliminary data. Galaxies at redshifts Z equals 10 and above, meaning galaxies that existed 400 to 600 million years after the Big Bang, were larger, brighter, and more structured than the standard model of galaxy formation predicted. In November 2022, a team led by Binghao Luo discovered several galaxy candidates at redshifts ranging from Z equals 11 to Z equals 20. If Z equals 20 is confirmed, this is a galaxy that existed approximately 180 million years after the Big Bang. 180 million years. This is vanishingly small in cosmological terms. A universe 180 million years old should still have been almost entirely dark, filled with primordial hydrogen and helium only beginning to form the first stars. And yet, in this data, there were galaxies. In February 2023, a study published in Nature attracted global attention. A team led by Ivo Labbé, an astronomer from Swinburne University, discovered 6 massive galaxies in Webb observations. The most massive of them contained, by estimates, up to 100 billion stars, comparable to our Milky Way, and existed less than 700 million years after the Big Bang. This was the moment when headlines began using the word crisis. But why is this a problem? Why do massive early galaxies violate the models? Let us now talk about the standard cosmological model, about lambda CDM, and what it predicted about early galaxy formation. Lambda CDM, lambda cold dark matter, is the standard model of cosmology. Lambda denotes the cosmological constant, dark energy. CDM stands for cold dark matter. This model is extraordinarily successful. It explains the cosmic microwave background, the large-scale structure of the universe, accelerated expansion, and the nucleosynthesis of the first elements. According to lambda CDM, galaxies form hierarchically. First, small structures. Small clumps of gas collapse under their own gravity and form the first small protogalaxies. Then, these small structures gradually merge to form larger ones. Large galaxies like the Milky Way form through billions of mergers of smaller predecessors. This process, hierarchical assembly, takes time, a lot of time. To form a galaxy containing 100 billion stars within 700 million years after the Big Bang would require converting matter into stars at a rate that significantly exceeds what we observe in any galaxy today. The star formation rate in a typical modern galaxy is a few solar masses per year. The Milky Way forms approximately 1 to 3 stars per year. To accumulate 100 billion stars in 700 million years at reasonable efficiency, you need a rate of about 150 to 200 solar masses per year, continuously, for hundreds of millions of years. Such rates of star formation are called starburst. They are observed in some galaxies, so-called starburst galaxies, but they are extreme and short-lived. They cannot be sustained for hundreds of millions of years under our current understanding of star formation physics. And yet Webb finds not one such galaxy, not 3, 6. In a single field of view, the probability that the lambda CDM model in its current form correctly describes what we see dropped sharply. Let us now talk about what the numbers specifically say, about the so-called galaxy number density, and why it is the most direct expression of the problem. In cosmology, there is a concept called the luminosity function. the distribution of galaxies by their brightness or mass at a given period of time. From this function, one can predict how many galaxies of a given mass should exist at a given moment in time. Lambda CDM makes specific predictions about the luminosity function in the early universe. At redshifts z equals 10 and above, there should be very few massive galaxies. Large galaxies essentially should not exist. They would not have had time to form. Webb discovers massive galaxies at z equals 10 and above in numbers 10 to 100 times exceeding the predictions of lambda CDM. This is not measurement error, not a systematic error of a factor of 1 or 2. This is a discrepancy of 1 to 2 orders of magnitude. When observations diverge from theory by an order of magnitude, this is not called an anomaly in physics. It is called a problem. This is why headlines use the words crisis and rewrites the textbooks. Not because journalists were exaggerating, because scientists, the scientists themselves, were using those words. Ivo Labbé, one of the authors of the key study, compared the situation to finding a dinosaur in a modern forest. It technically violates no laws of nature, but it sharply contradicts our understanding of how the world works. Let us now talk about the possible explanations, about what astrophysicists are proposing to resolve this contradiction. Explanation 1. We are incorrectly estimating distances. Redshift is our primary tool for estimating distance to distant galaxies. The higher the redshift, the further the object. But redshift is measured from a spectrum, from how specific spectral lines are shifted toward the red end. For very distant objects, where we don't have sufficient spectral data, redshift is estimated photometrically, by the brightness of the object through different filters. This is a less precise method. Some objects that appear very distant based on their photometric redshifts may actually be closer. Their redshifts are overestimated. This is a real possibility. And indeed, when some of Webb's candidates received spectroscopic confirmation, which gives much more precise redshifts, some turned out to be at slightly lower redshifts than assumed. But not all. Many were confirmed exactly where expected. Explanation 2. We are incorrectly estimating galaxy masses. The mass of a galaxy is estimated from its total luminosity. We know roughly what luminosity one star of a given type has. We multiply by the number of stars and get an estimate. But if the earliest galaxies contained significantly more very massive and very bright stars, so-called population 3 stars, the first generation of stars made from nearly pure hydrogen and helium, then we may be systematically overestimating total stellar mass. Because we apply calibrations based on modern stellar populations to stellar populations that were fundamentally different, population 3 stars were significantly more massive than modern stars. Their luminosity per unit mass was different. If early galaxies were dominated by them, their apparent stellar mass based on luminosity would be overestimated. Explanation 3. Star formation in the early universe was significantly more efficient than we thought. Current models of star formation predict that only a few % of a gas cloud's mass converts into stars. The rest is heated and dispersed by the radiation and winds of young stars. If efficiency was significantly higher in the early universe, say 10 to 20% instead of 1 to 3, then stellar mass accumulated faster. Massive galaxies could have formed sooner. What could have provided higher efficiency? In the early universe, interstellar gas was colder and denser. Metallicity was low, fewer heavy elements that can heat gas and impede collapse. These factors theoretically favor more efficient star formation. Explanation 4. Dark matter behaves differently than in the standard model. Lambda CDM assumes dark matter is cold, slowly moving, forming hierarchical structures from the bottom up. But there are alternative dark matter models that predict different structure. For example, warm dark matter that forms larger initial structures immediately. If dark matter halos formed faster in the early universe, gas within them collapsed faster, stars formed faster. Large galaxies could have appeared earlier. Explanation 5, the most radical. The standard cosmological model is fundamentally incomplete or incorrect. Lambda CDM is the best model we have, but this does not mean it is correct. Physics has a history of models that were extraordinarily successful in their domain of application, but required replacement when that domain expanded. Newtonian mechanics was perfectly accurate for slow objects in weak fields. Special relativity was necessary for fast objects, general relativity for strong fields. Perhaps Lambda CDM is a good approximation for most of the universe's history, but needs extension or replacement for describing the very earliest epochs. Let us now talk about the cosmic microwave background, about what it tells us about the constraints within which any model must operate. The cosmic microwave background, CMB, is light emitted approximately 380,000 years after the Big Bang, when the universe first became transparent. Before that moment, the universe was so hot that photons could not travel freely. When it cooled sufficiently, photons broke free. This moment is called recombination. The CMB is measured with extraordinary precision. Temperature fluctuations in the CMB, tiny variations in its intensity in different directions, reflect the density fluctuations of the universe at 380,000 years. These fluctuations are the seeds from which all subsequent structures grew: galaxies, clusters, the filaments of large-scale structure. Lambda CDM makes precise predictions about the CMB, and they agree with observations superbly. The Planck Space Telescope measured the CMB with unprecedented precision. Agreement with Lambda CDM is excellent. This means Lambda CDM cannot simply be discarded. It correctly describes the early conditions of the universe and large-scale structure. Any modification to the model must preserve this agreement with the CMB. This is a strong constraint. It means explanations for early massive galaxies must be compatible with very precise predictions about density fluctuations in the CMB. You cannot simply add more dark matter or faster star formation without violating other predictions. This makes the problem sharper rather than less so. Let us now talk about the specific data from Webb that are most striking, about the observations that are most difficult to explain within existing models. In July 2022, in Webb's first public data, the deep field image SMACS 0723 was published. This was an image of an area of sky covering an angular size roughly equal to a grain of sand held at arm's length. In a few hours of observation, the telescope discovered thousands of galaxies. Some of them, through gravitational lensing by the SMACS 0723 cluster, were magnified and appeared to be at redshifts Z equals 8 to 9. But the truly troubling results came from specialized deep survey programs. The CEERS program, Cosmic Evolution Early Release Science Survey, the first major Webb observational program, surveyed a portion of sky previously studied in detail by Hubble, the extended growth strip field. In this data, the series of high redshift galaxy candidates was identified, including those 6 massive early galaxies from Labbé's study. The JADES program, JWST Advanced Deep Extragalactic Survey, one of Webb's most extensive deep field programs, is accumulating data that will be analyzed for years. In this data, galaxies have already been identified at Z equals 13 to 14. The galaxy JADES-GS-Z14-0, confirmed in 2024, existed approximately 290 million years after the Big Bang. It is one of the most distant spectroscopically confirmed objects ever discovered. What makes JADES-GS-Z14-0 particularly remarkable? Its size. This galaxy has a significantly larger angular size than expected for an object at such a redshift. This indicates it was already physically large, not just bright, very early in the history of the universe. Let us now talk about what the scientific literature has said in response, about how the professional community has reacted to Webb's data over the last 2 years. The scientific community's reaction followed a characteristic path. First wave, mid-2022 to early 2023, surprise and preliminary analysis. Preprints appeared rapidly. Some made strong claims. Headlines screamed about a crisis in cosmology. Scientists themselves experienced genuine surprise. Second wave, 2023, reassessment. More careful analysis showed that some initial redshift estimates were overestimated. Spectroscopic confirmations provided more accurate data and lowered some estimates. Statistics were refined. Systematic errors were better characterized. Third wave, 2024 and beyond, synthesis. Does the problem remain after all refinements? Most researchers say yes, though in softened form. The number of excess early massive galaxies is smaller than initially seemed, but it still exceeds standard predictions, not by a factor of 100, but by a factor of 10 to 20 in some mass ranges at some redshifts. Specific studies of 2023 to 2024, work by Stephen Finkelstein and colleagues, 2023, based on CEERS data, showed that the luminosity function at Z greater than 10 exceeds predictions by a factor of about 10. This is a problem, but potentially solvable if star formation efficiency in the early universe was higher. Work by Kyla D'Aloisio and colleagues showed that some of the early bright galaxies may contain active galactic nuclei, supermassive black holes actively accreting matter, which would additionally increase their apparent brightness. Simulation work, attempts to modify star formation model parameters to reproduce Webb's observations, showed that some physical processes were underestimated in previous models. Let us now talk about the specific observational phenomenon that is most important for understanding why early galaxies are such a problem, about dark matter halos, and why their growth rate limits galaxy growth rates. In the standard model, galaxies form inside so-called dark matter halos. Dark matter concentrates into spherical structures called halos. Normal matter, baryonic matter, gas, stars, planets, falls into these gravitational wells and forms visible galaxies at the center of each halo. The growth of dark matter halos is determined by the initial density fluctuations in the early universe, precisely those recorded in the CMB. Halos grow hierarchically, small ones first, large ones later through mergers. This creates a fundamental pace. The growth rate of dark matter halos limits the growth rate of galaxies. You cannot have a galaxy more massive than its dark matter halo, and halos cannot grow faster than the initial conditions allow. This is precisely what puts Webb's early massive galaxies in a difficult position. Even if star formation proceeds at 100% efficiency, an absurdly high value, and all gas within the halo instantly converts to stars, the halo at Z equals 10 simply has not accumulated enough mass for a galaxy of 100 billion stars. This constraint does not come from poorly understood star formation physics. It comes from the initial conditions established by the CMB. It is rigid. If galaxies truly exist that massive, that early, either our mass estimates are wrong, which is possible, or something in the early universe violated hierarchical halo assembly, which requires new physics, or we fundamentally misunderstand something about early epochs. Let us now talk about something that connects all of Webb's discoveries to the deepest philosophical question, about what these observations tell us about the nature of scientific knowledge. When people hear that Webb calls models into question, or that galaxies have been found that should not exist, a common reaction is, this means science knows nothing, or everything we were told was a lie. This is a wrong interpretation. Lambda CDM is one of the most precisely tested theories in the history of physics. Its predictions about the cosmic microwave background agree with observations to within fractions of a percent. Its predictions about the ratio of primordial elements agree with observations with high precision. Its predictions about the large-scale structure of the universe, the filaments, walls, and voids, are reproduced in simulations and confirmed by observations. This is not a model that knows nothing. This is a model that knows a great deal and that has specific areas where knowledge is incomplete. Science advances precisely by identifying such areas. Newtonian mechanics was complete and self-consistent in its domain of application, until observations appeared that did not fit. Then relativity emerged, not refuting Newton, in his domain he is still correct, but expanding understanding. Lambda CDM is in an analogous position. Webb's early galaxy problem is not a refutation of the model. It is an indication of an area where the model needs expansion or refinement. What exactly will be needed? More precise understanding of star formation feedback, refinement of dark matter properties in the early universe, possibly new physics in inflation, we do not know. But we know that Webb has pointed us in a specific direction where new physics may be found. This is science in its healthiest form. An instrument better than any previous one points to a specific area of the unknown. Scientists investigate that area. Understanding deepens. Let us now talk about the early universe phenomenon that is most directly connected to Webb's galaxy discoveries, about the epoch of reionization, and why the galaxies Webb is finding are the key to understanding one of the most significant transitions in cosmic history. After recombination, 380,000 years after the Big Bang, when the universe became transparent, an epoch called the Dark Ages began. The hydrogen of the universe was neutral. Neutral hydrogen absorbs ultraviolet radiation. This meant the universe was opaque to ultraviolet light. The first stars that formed during this period, approximately 100 to 300 million years after the Big Bang, began emitting ionizing ultraviolet radiation. This radiation gradually ionized the surrounding neutral hydrogen, converting it back into protons and electrons. This process is called reionization. Reionization did not happen instantaneously. It took several hundred million years, roughly from Z equals 15 to Z equals 6, from about 270 million years to about 900 million years after the Big Bang. By Z equals 6, the universe was essentially completely reionized. Intergalactic hydrogen became ionized again and transparent to ultraviolet. Who produced reionization? This is one of the open questions of astrophysics. The main candidates: early galaxies with their young hot stars emitting ionizing radiation, or quasars, active galactic nuclei with accreting black holes producing powerful radiation. Data indicates that early galaxies, small faint galaxies that existed in large numbers, are likely the primary source of reionizing radiation. But in large numbers is the key. Enough galaxies with enough ionizing radiation is required. And here Webb's early galaxy problem directly connects to reionization. If there were significantly more massive early galaxies at Z equals 10 to 15 than lambda CDM predicts, this means there was also more ionizing radiation during the epoch of reionization. Reionization may have occurred earlier or been more efficient than we thought. Let us now talk about the specific scientific program that is most ambitious among all that Webb is conducting, about the search for atmospheres around planets in the TRAPPIST-1 system and how far this research has progressed. TRAPPIST-1, a red dwarf 39 light-years away with 7 Earth-sized planets, 3 of which are in the habitable zone, is a priority target for the search for life beyond the solar system. Webb began systematic study of TRAPPIST-1 planets in 2022 to 2023. By mid-2024, results have been published for several planets. TRAPPIST-1b, the innermost planet, not in the habitable zone, was characterized first. The thermal emission from its day side is inconsistent with a dense CO2 atmosphere. The planet may lack an atmosphere entirely. TRAPPIST-1c, the second planet from the star, also not in the habitable zone, showed dayside thermal emission lower than expected for a bare rock. This may indicate the presence of a thin atmosphere, but the interpretation is ambiguous. TRAPPIST-1e, F, G, the habitable zone planets, are the most difficult to observe. Their angular size is smaller, the signal from their atmospheres is weaker. Observations are ongoing. The fundamental point: Webb is the first instrument capable of even attempting this first step for Earth-sized planets in habitable zones of real stars. Before Webb, this was impossible. Let us now talk about what is happening right now in the scientific conversation about Webb's discoveries, about the current state of research and what is being published and debated. Since Webb began science operations in mid-2022, the pace of discovery has been extraordinary. More than 1,000 peer-reviewed papers citing Webb data were published in its first year of science operations alone. Several threads in the current scientific conversation. The little red dots, a population of compact red sources discovered by Webb at redshifts Z equals 4 to 9 that appear to be active galactic nuclei with masses of supermassive black holes larger than expected. Their number density significantly exceeds predictions. This is a parallel problem to the early massive galaxy problem: too many massive black holes too early. The Hubble tension intersection. Webb measured distances to Cepheid variable stars in several galaxies with its infrared capability, providing an independent check on the local value of the Hubble constant. Result: the local value of the Hubble constant remains high at about 73 kilometers per second per megaparsec, consistent with previous measurements that disagree with the CMB inferred value of about 67. Webb did not resolve the Hubble tension. It confirmed it is real. Population 3 star candidates. Webb has identified several objects that show spectral features consistent with extremely hot, massive first-generation stars. None are definitively confirmed. But the existence of candidates is progress. Before Webb, searching for population 3 stars was purely theoretical. Each of these threads adds to a picture that is more complex and more rich than what we had before Webb. Each requires refinement of models. Each points towards specific areas of incomplete understanding. Let us now talk about the specific tools Webb has that make its contributions to this science uniquely powerful, about NIR spec and what simultaneous spectroscopy of many objects changes about the scale of possible research. NIR spec, the near-infrared spectrograph, is one of Webb's 4 main scientific instruments. Its key feature, the ability to simultaneously obtain spectra from 100 objects in a single field of view. A spectrum is the decomposition of an object's light by wavelength. It contains incomparably more information than an image. From a spectrum, you can extract precise redshift and therefore distance, chemical composition of the atmosphere or interstellar gas, temperature, velocity. Before Webb, obtaining the spectrum of a single distant object required many hours of observation on the largest ground-based telescopes. Obtaining spectra of hundreds of objects in a deep field was a multi-year project. NIRSpec, with its microshutter assembly, a matrix of 250,000 tiny individually controlled shutters, allows obtaining spectra from 100 objects simultaneously in a single observation. That takes hours rather than years. This changes not only the speed of research, it changes the very possibility of obtaining statistically significant samples at high redshifts.
Instead of confirming the redshifts of a few of the brightest candidates, Webb can obtain spectra of hundreds of galaxies in a single survey field. This creates statistics. This allows building a reliable luminosity function at z greater than 10. This produces real science rather than isolated, intriguing observations. Let us now talk about the most personally immediate thing, about what you can actually do tonight to connect with everything we have discussed. Webb is currently at the L2 Lagrange point, 1.5 million kilometers from Earth in the direction opposite the Sun. It cannot be seen with the naked eye, it is too small and too distant, but its field of view is the actual sky above you, the same stars, the same dark depth between them. In that dark depth, invisible without instruments, revealing itself only in infrared data from many hours of observation, galaxies. Thousands of galaxies in every tiny square of sky,
some of them existing when the universe was less than 500 million years old. The specific area of sky Webb observes changes as the telescope is repointed for different programs, but the principle remains. That darkness you see between the stars is not empty. It is full of galaxies stretching back to nearly the beginning of time. The photons that left those early galaxies, 13.5 billion years ago, when no star like our Sun existed anywhere, when there were no rocky planets, no possibility of life, those photons have been traveling through expanding space ever since, through the Dark Ages, through reionization, through the formation of our galaxy, through the formation of our solar system, through the evolution of life, through the emergence of minds. And they are arriving now, at Webb's mirror, being captured, being converted into data, being analyzed. Right now, while you look up, that is what is happening in the dark between the stars above you. Let us talk about something that is both technically specific and deeply disorienting, about what it actually means for a galaxy to be too massive, too early, and why this specific problem is harder to dismiss than it first appears. The standard model of structure formation is not arbitrary. It is derived from first principles, from the equations of general relativity applied to an expanding universe filled with dark matter, baryonic matter, and dark energy, with initial conditions set by the quantum fluctuations of inflation that are recorded in the CMB. These equations make specific quantitative predictions, not general predictions like galaxies will form eventually or large structures take time to assemble, specific numerical predictions. At redshift Z, in a co-moving volume V, the number of galaxies more massive than M should be N, with specific uncertainties derived from the uncertainty in cosmological parameters.
Webb's observations can be directly compared to these predictions, and the comparison shows a discrepancy that cannot be hidden in the uncertainties. Here is the specific form of the problem. To have a galaxy containing 10 to the 11th power solar masses in stars at Z equals 7.5, roughly 700 million years after the Big Bang, you need to have assembled that stellar mass within the available time. The universe at that epoch contains a certain amount of baryonic matter per unit volume. Dark matter halos of a certain maximum mass exist at that epoch. The fraction of baryonic matter that can realistically collapse into stars within those halos is constrained by known physics. Running these numbers through the standard model, you get a predicted number of galaxies above 10 to the 11th solar masses at Z greater than 7 per unit volume. Webb has surveyed specific volumes and found more of these objects than the prediction allows. Not ambiguously more, significantly more. The tension is not at the level of 10 or 20%, which could be resolved by tweaking parameters within the model. It is at the level of factors of 10 or more, which requires something outside the parameter space of the current model. This is why the problem is taken seriously by the community, not because journalists hyped it, because the numbers are clear and the discrepancy is large. Let us now talk about the specific candidate explanation that has gained the most traction in the scientific literature, about the role of feedback and what happens when you change how it operates in models of the early universe. Feedback is the process by which star formation regulates itself. When stars form, they emit radiation, produce stellar winds, and eventually explode as supernovae. All of this energy heats and disperses the surrounding gas, slowing or stopping further star formation. This is negative feedback. It limits how efficiently gas converts to stars. In modern galaxies, feedback is extremely efficient. Star formation efficiencies are typically 1 to 3%, meaning only 1 to 3% of the available gas in a molecular cloud converts to stars before feedback disperses the rest. The critical question: was feedback as efficient in the early universe? In the early universe, the interstellar medium had very low metallicity. Heavy elements, carbon, oxygen, iron, everything heavier than helium, are produced by stars and spread by supernovae. The first galaxies were made of nearly pure hydrogen and helium. This matters for feedback in several ways. First, dust. Radiation pressure from young stars acts primarily through dust grains. Photons are absorbed by dust and transfer momentum to it, which then drags the gas. Without dust, this mechanism is much less effective. The early, low metallicity interstellar medium had very little dust. Feedback from radiation pressure was weaker. Second, metal line cooling. Gas cools primarily by radiating energy away through emission lines of metal atoms. Without metals, the gas cools less efficiently. This sounds bad for star formation. Warmer gas is harder to collapse. But for feedback, gas that cannot cool efficiently also cannot radiate away the energy injected by supernovae as effectively, meaning supernova energy goes into dispersing the gas rather than being radiated away. The net effect on feedback efficiency is complex and is one of the actively debated aspects. Third, the initial mass function may have been different. The IMF is the distribution of stellar masses at birth, how many low-mass stars versus high-mass stars form from a given cloud. In the early universe, theoretical predictions suggest the IMF was top-heavy, more high-mass stars relative to low-mass stars. High-mass stars are more luminous and die faster, as supernovae, so a top-heavy IMF means more intense feedback per unit stellar mass. This third point cuts both ways. More intense feedback from a top-heavy IMF would suppress star formation, but it would also make the surviving stellar population appear more luminous per unit mass, making galaxies appear more massive than they are from their light. The current best guess from theorists, some combination of reduced feedback efficiency and top-heavy IMF in early galaxies can explain a significant portion of the excess Webb sees, but not all of it. The problem is real, just likely less severe than initial estimates suggested. Let us now talk about the specific object that is the most scientifically interesting single target in Webb's early universe program, about JADES-10
JADES-Z14-0 and what makes it uniquely informative. JADES-GS-Z14-0 was spectroscopically confirmed in 2024 as existing at Z equals 14.32, approximately 290 million years after the Big Bang. It is among the most distant spectroscopically confirmed objects ever observed. What makes it special beyond its distance? Its luminosity. This galaxy is bright, far brighter than models of early galaxy formation predicted should be possible at this epoch. Its luminosity implies a very high star formation rate, or a top-heavy stellar population, or both. Its size. Unlike many high redshift galaxies that appear as point sources even to Webb, JADES-GS-Z14-0 is spatially extended. It has measurable angular size. From this size and its redshift, the physical size can be calculated, approximately 1,700 light-years in radius. This is not a tiny protogalaxy. It is a substantial structure. Its chemical enrichment. The spectrum of JADES-GS-Z14-0 shows emission lines from oxygen, meaning the galaxy already contains heavy elements produced by previous generations of stars. This is remarkable at 290 million years after the Big Bang. It means multiple generations of stars had already lived and died in this galaxy. Stars had to form, evolve, explode as supernovae, enrich the interstellar medium, and then new stars had to form from this enriched gas. All within 290 million years. This timescale is extremely compressed. It implies either very rapid star formation from the very beginning, or that star formation began extremely early, possibly within the first 100 to 150 million years after the Big Bang. Neither option is comfortable for standard models. Both are actively being studied. Let us now talk about something that puts the Webb discoveries in the broadest possible context, about what we are actually doing when we observe the early universe, and why this is philosophically significant. Light is the only messenger we have from the distant universe. Everything we know about objects more than a few hundred light years away, we know because photons left those objects and eventually arrived at our detectors. The photons arriving from JADES-GS-Z14-0 left that galaxy approximately 13.5 billion years ago. At that time, our Sun did not exist. It would not form for another 9 billion years. The Milky Way did not exist in its current form. The raw material for it was scattered across a region of primordial gas. Earth did not exist. No rocky planet anywhere in what would become our cosmic neighborhood existed. The interstellar medium had not yet been sufficiently enriched with the heavy elements needed to form rocky bodies. Life, as far as we know, did not exist anywhere in the observable universe. The conditions for life as we understand it require the products of many generations of stellar nucleosynthesis. And yet those photons have been traveling ever since, through 13.5 billion years of cosmic history, through epochs we can only observe with the most powerful instruments humanity has ever built, through the formation of our galaxy, our star, our planet, through the entire history of life on Earth, through all of human civilization. They arrived at Webb's mirror in 2022, and they told us something unexpected. The galaxy they came from was already large, already chemically enriched, already bright, at a time when everything we thought we knew said it should be small, primitive, and faint. This is not a failure of science. This is science doing exactly what it is supposed to do, confronting our models with reality and discovering where the models need to grow. Let us now talk about the specific technological achievement that makes Webb's observations possible, about the mirror alignment process, and why it was one of the most demanding engineering accomplishments in the history of spaceflight.
Webb's primary mirror consists of 18 hexagonal gold-plated beryllium segments, each about 1.32 meters across. These segments were folded for launch. The full 6.5-meter mirror would not fit inside the Ariane 5 rocket fairing. After reaching L2, the segments had to be unfolded and aligned with extraordinary precision. The requirement? Each mirror segment must be positioned so that all 18 segments act as a single continuous mirror. The alignment precision required is measured in nanometers, billionths of a meter. Each segment has 6 actuators on its back that can move it with nanometer precision. In total, Webb has 132 actuators controlling its mirror's shape. The alignment process took approximately 3 months after launch. Engineers used a star as a reference. Each mirror segment formed its own separate image of the star, producing 18 separate spots in the detector. The actuators were then adjusted iteratively in a process called wavefront sensing and control, until all 18 images merged into one sharp point. The final alignment achieved a wavefront error of approximately 150 nanometers, slightly better than the requirement. This corresponds to the mirror's surface being shaped to within a fraction of the diameter of a human red blood cell across a structure 6.5 meters wide. For infrared astronomy, this precision is not an aesthetic achievement. It directly determines how much of the light from a distant galaxy is concentrated into the detector pixel versus spread across neighboring pixels. Better concentration means more signal from faint objects, which means seeing further back in time. The alignment that took 3 months to achieve in early 2022 is the foundation on which every scientific result Webb has produced since then is built, including every galaxy at Z greater than 10, including JADES-GS-Z14-0, including the early massive galaxy problem. Let us now talk about what happens to Webb's infrared light, about the specific detectors that capture the photons and what makes them so sensitive. Webb's infrared detectors are made of mercury-cadmium telluride, HGCdTe, a semiconductor that is sensitive to infrared photons. These detectors must be cooled to extremely low temperatures to eliminate the thermal noise that would otherwise swamp the faint infrared signals from distant galaxies. The NIR-CAM and NIR-SPEC instruments operate at about 37 Kelvin, roughly minus 236 degrees Celsius. At this temperature, the thermal emission from the detector itself is so low that the detector noise is dominated by the quantum noise from individual photon arrivals, the Poisson statistical fluctuation in how many photons arrive per unit time. This is the fundamental limit of sensitivity for a given collecting area and observation time. The MIRI instrument, the mid-infrared instrument, requires even colder temperatures, 6.4 Kelvin, achieved by an active cryocooler. At 6.4 Kelvin, MIRI can detect mid-infrared radiation from objects at the most extreme redshifts. Galaxies so far away that their ultraviolet light has been redshifted all the way into the mid-infrared. These detectors, when operating at their design temperatures, are among the most sensitive optical and infrared detectors ever operated in space. Each 2048 by 2048 pixel array can record the arrival of individual photons with high efficiency. When JADES-GS-Z14-O's light arrives at these detectors, a stream of individual infrared photons that has been traveling for 13.5 billion years, each photon converts an electron in the semiconductor from the valence band to the conduction band. This tiny electrical signal is amplified, digitized, and transmitted to Earth. Scientists then reconstruct from millions of such individual photon events the structure and spectrum of that distant galaxy. The entire chain, from a photon emitted in a galaxy 13.5 billion years ago to a number in a dataset on a scientist's computer,
involves nothing magic, just physics, engineering, and the extraordinary precision of human craftsmanship applied over decades. Let us now talk about the specific next telescopes that will follow Webb, about the observational future that Webb's discoveries have made more urgent. The Extremely Large Telescope, ELT, the 39-metre ground-based telescope being built in Chile by ESO, will have angular resolution far exceeding Webb's in the infrared when using adaptive optics. While Webb detects galaxies at Z greater than 10, often as point sources or barely resolved patches, ELT will be able to resolve their internal structure, where stars are forming within them, how gas is moving, where the dark matter is concentrated. First light for ELT is expected around 2028.
Within a few years of operation, ELT will be obtaining detailed spectra of objects Webb has identified, probing their chemical composition, velocity structure, and star formation histories with a level of detail that is currently impossible. The Nancy Grace Roman Space Telescope, launching around 2027, has the same mirror diameter as Hubble, but a field of view 100 times larger. Roman will conduct wide area surveys, finding rare objects like the most massive early galaxies across huge areas of sky, building the statistical samples needed to rigorously measure the luminosity function at high redshifts. Where Webb goes deep and narrow, detecting faint galaxies in small fields, Roman will go wide and moderately deep, finding the brightest representatives of rare populations across much larger volumes. The combination of Webb, Roman, and ELT in the late 2020s and 2030s will provide complementary views of the early universe at a level of detail we cannot currently access.
The problem of early massive galaxies will either be explained or sharpened to the point where new physics becomes unavoidable. Let us now talk about what the question of early massive galaxies means when placed in the context of the broader scientific narrative, about why this particular puzzle matters beyond its technical specifics. The story of structure in the universe is the story of how everything we know came to exist. The universe began in a state of extraordinary uniformity, nearly perfectly smooth, with only tiny quantum fluctuations in density from the inflationary epoch. These tiny fluctuations, amplified by billions of years of gravitational collapse, became everything: stars, galaxies, galaxy clusters, the cosmic web of filaments and voids that structures the observable universe. We can observe the beginning of this story in the CMB. We can observe the end of this story, the present-day universe, in our own galaxy and its neighbours. The chapter in between, how the smooth early universe became the lumpy, structured present, is what Webb is exploring. Getting this chapter right matters because it is where all causality runs through. The specific way that the first structures formed determines the chemical enrichment history of the universe, which elements were available when and where for planet formation. It determines the merger history of galaxies, how the Milky Way came to be the galaxy it is. It determines the cosmic star formation history, when and where most stars formed, which determines how many planetary systems exist in the universe. If the earliest chapter is wrong, if galaxies really did form more massively and earlier than our models say, then downstream in the story there are corrections needed throughout. The chemical enrichment history was faster. The heavy elements needed for rocky planets and for life were available sooner. The universe may have been habitable, in the sense of having the heavy elements necessary for Earth-like chemistry, earlier than we thought. This is not directly about life, but it is about the conditions for life. The story of early galaxies is part of the story of how the universe became capable of producing something like us. Getting that story right matters. Let us now talk about what the specific observational signatures of the early universe look like, about the colours and shapes of galaxies in Webb's deep fields and what they tell us directly. In Webb's deep field images, the most distant galaxies are red. This is not because they are red in any intrinsic sense. It is because their light has been so heavily redshifted that only the longest wavelength light that Webb can detect, the reddest infrared, is still detectable from them. Their bluer light has been shifted entirely beyond Webb's sensitivity range. This is a direct visual representation of cosmological history.
The redder a galaxy appears in a Webb infrared image, the earlier in cosmic history it existed. The most extreme red galaxies in Webb's deep fields are the earliest. The shapes of early galaxies tell their own story. Many of the early massive galaxy candidates discovered by Webb appear compact, smaller than galaxies of similar mass in the present universe. This compactness is itself informative. It tells us that these galaxies had not yet undergone the late merging events that spread stellar mass into the extended outer regions of modern galaxies. Some early galaxies appear clumpy, not the smooth disks of modern spiral galaxies or the smooth ellipsoidal shapes of modern ellipticals, but irregular, clumped structures that suggest active, chaotic star formation rather than settled dynamical equilibrium. This is what you would expect of galaxies that are still actively assembling.
Webb's infrared imaging allows these morphological studies at redshifts where Hubble could barely detect objects at all. The structural information that Hubble provided for galaxies at z equals 1 to 3, when the universe was 2 to 5 billion years old, Webb is now providing for galaxies at z equals 6 to 14, when the universe was only 400 million to 1 billion years old. This is a shift in temporal coverage of about 4 billion years of cosmic history. That is more time than Earth has existed. Let us now talk about the specific way that gravitational lensing amplifies Webb's view of the early universe, about the cosmic telescopes that the universe itself provides. Massive clusters of galaxies bend spacetime. Light from objects behind the cluster, much farther away, follows the curved spacetime and is deflected. The result is that distant background galaxies are magnified and sometimes distorted into arcs or rings around the foreground cluster. Webb observes several massive clusters specifically to exploit this gravitational lensing effect. The cluster acts as a natural lens, boosting the apparent brightness of background galaxies by factors of 10, 100, or even more in extreme cases. This allows Webb to see galaxies that would otherwise be too faint to detect, pushing the accessible redshift range even further. Some of the most extreme redshift objects in Webb's catalogue were discovered through gravitational lensing magnification. The iconic first deep field image of SMAC SO723 was specifically chosen as a target because this massive cluster provides exceptional lensing of background galaxies. The arcs and distorted shapes visible throughout that image are not the cluster galaxies themselves. They are much more distant background galaxies whose light has been bent and magnified by the cluster's gravity. This technique, using massive clusters as gravitational telescopes, allows Webb to effectively increase its mirror size beyond its physical 6.5 meters by exploiting natural amplification. For certain objects and certain lines of sight, Webb combined with a lensing cluster has effective collecting power equivalent to a much larger mirror. It is one of the most elegant aspects of cosmological observation, using the massive structures of the universe itself as tools to peer even further into its own history. Let us now talk about the specific question that Webb raises about our own cosmic address, about where the Milky Way fits in this story, and what these early massive galaxies mean for our galaxy's own history. The Milky Way is a relatively large galaxy. Its total mass, including dark matter, is approximately 10 to the 12th power solar masses. Its stellar mass is roughly 5 to 6 times 10 to the 10th power solar masses, around 50 to 60 billion stars. Where did the Milky Way come from? Like all large present-day galaxies in the Standard Model, it assembled hierarchically through the merger of many smaller predecessors over billions of years. The oldest stars in the Milky Way's halo, the ancient metal-poor stars in globular clusters, are 13 to 13.5 billion years old. They formed in some of the first small proto-galaxies that would eventually merge to build our galaxy. The Gaia spacecraft, which is mapping the positions and velocities of about 1.5 billion Milky Way stars with extraordinary precision, has revealed evidence of major merger events in the Milky Way's history. The Gaia-Enceladus merger, a large dwarf galaxy that the Milky Way absorbed about 8 to 11 billion years ago, left a distinctive kinematic signature in the velocities of halo stars. Webb is observing the progenitors of galaxies like the Milky Way at the redshifts when these building blocks existed. Galaxies at Z equals 4 to 8, with masses of a few times 10 to the 9th solar masses, are candidates for the kinds of proto-galactic fragments that would eventually merge to form systems like ours. By studying these progenitors, their chemical composition, their star formation rates, their structural properties, Webb is tracing the family tree of our own galaxy. This is personal history. The stars in those distant galaxies whose light is arriving at Webb right now include some that may have had planets, some that may have contributed their supernova ejector to the cloud that would eventually form the Sun. Those distant galaxies are in some real sense our ancestors. Let us now talk about the specific discovery that has the most direct bearing on the question of life in the universe, about what Webb's atmospheric characterization of exoplanets has revealed about the diversity of worlds. Webb has obtained atmospheric spectra for several exoplanets, mostly gas giants and mini-Neptunes, that are easier to characterize than Earth-sized rocky planets. WASP 39b, a hot Saturn-mass planet, was one of the first exoplanet atmospheres analyzed in depth by Webb. In its spectrum, Webb detected carbon dioxide, CO2, with higher signal-to-noise than any previous detection, sulfur dioxide, SO2, the product of photochemical reactions in the upper atmosphere. This was the first detection of photochemical processes in an exoplanet atmosphere, analogous to the photochemical smog production in Earth's atmosphere, but at high temperatures. Water vapor, H2O, carbon monoxide, CO, sodium, Na, and potassium, K. This richness of chemical species in a single spectrum, obtained in one observing program, demonstrated that Webb can probe atmospheric chemistry in detail that was not previously achievable. For Earth-like planets in habitable zones, the specific molecules of interest are biosignatures: oxygen, O2, ozone, O3, methane, CH4, in combination with oxygen, because this combination requires biological replenishment. It cannot persist without it. Nitrous oxide, N2O, and others. K2-18b, a sub-Neptune 120 light-years away in the habitable zone of its red dwarf star, is a particularly interesting target. Webb's spectrum of K2-18b shows methane and CO2, consistent with a Hycean world interpretation, a world with a liquid water ocean under a hydrogen-rich atmosphere. A tentative detection of dimethyl sulfide, DMS, produced only by biological processes on Earth, was reported but has not yet been confirmed to the standard statistical threshold. The significance. Webb has opened the era of atmospheric chemistry for potentially habitable worlds. We are not yet detecting biosignatures, but we have the instrument that could detect them. The next decade of Webb observations of nearby habitable zone planets, TRAPPIST-1, LHS 1140, K2-18, will tell us whether any of these worlds show chemical signs of biology. This is not guaranteed, but it is now possible. That possibility did not exist before Webb.
Let us now talk about what all of this means when taken together, about the unified picture that Webb is building across its different scientific programs. Webb is simultaneously looking at the earliest epochs of the universe, finding galaxies that existed 200 to 300 million years after the Big Bang, and discovering that they are more massive and more numerous than our models predicted. Watching the middle of cosmic history, observing galaxies at z equals 2 to 5 as they grow and merge and form the large structures of the present universe. Examining the recent universe, our own galactic neighborhood, with unprecedented infrared clarity, mapping star-forming regions, studying the composition of nearby galaxies, characterizing the atmospheres of planets orbiting nearby stars. These are not separate programs that happen to share a telescope. They are connected investigations of a single continuous story, the 13.8 billion-year history of structure and chemistry and, ultimately, life in the universe. The early galaxy problem connects to the epoch of reionization, which connects to the formation of first heavy elements, which connects to the enrichment of later galaxies, which connects to the formation of rocky planets, which connects to the possibility of atmospheric chemistry and biosignatures around nearby stars. Pull on any thread and the whole story comes with it. Webb is pulling multiple threads simultaneously, and the picture that is emerging, rich, detailed, surprising, sometimes contradictory, always deeper than what was visible before, is the most detailed we have ever had of how the universe arrived at the moment where something on a small rocky planet around an ordinary star became capable of building Webb and pointing it at the beginning of time. Let us talk about something that is both technically specific and personally resonant, about the specific moment in July 2022 when the first Webb images were released, and what that moment represented. On July 12, 2022, President Biden unveiled the first Webb science image at the White House, the deep field of SMAC SO723. It was the deepest infrared image of the universe ever taken at that point. The image shows thousands of galaxies in an area of sky smaller than a grain of sand held at arm's length. Some of those galaxies are elliptical, some spiral, some irregular. Some appear distorted into arcs by gravitational lensing. Some are so distant that their light has been traveling for more than 13 billion years to reach us. The next day, 4 more images were released: the Carina Nebula, the Southern Ring Nebula, Stephan's Quintet, and the first exoplanet atmospheric spectrum from WASP 96b. Scientists who had spent their careers working toward Webb, some for 25 years or more, described the experience of seeing the first images as overwhelming. Not in a controlled professional sense, actually emotionally overwhelming. Tears. Not because the images are beautiful, though they are, because they represent the culmination of something. A generation of engineers and scientists and administrators and politicians and public supporters who sustained a project through budget overruns, technical crises, schedule delays, pandemic, and eventually watched a machine they spent decades building unfold perfectly in space and begin returning data that exceeded expectations. Jane Rigby, Webb's operations project scientist, described looking at the first deep field and realizing that it contained galaxies Webb was not designed to see, that the sensitivity achieved was beyond specification, that the telescope was performing better than anyone had guaranteed it would. This is what extraordinary engineering looks like from the inside, not a clean success story. Decades of uncertainty and problem solving, and then a moment when the instrument works better than promised. And then it immediately found galaxies that should not exist. That tension, the extraordinary achievement of Webb, followed immediately by the extraordinary puzzle of what it found, is the defining character of the mission's first years.
Let us now talk about the specific technical reason Webb exceeded its design specifications, about why it arrived at L2 with more fuel than expected, and what this means for the mission's longevity. Webb launched on an Ariane 5 rocket on December 25, 2021. The rocket performed with exceptional accuracy, delivering Webb to a trajectory so precise that the mid-course correction burns needed only a fraction of the fuel that had been conserved for this purpose. The accuracy of the launch trajectory directly affects how much fuel is needed for the mid-course corrections that place Webb accurately at L2. Because the launch was so accurate, these corrections used far less fuel than the worst-case scenarios that had been planned for. The fuel saved goes directly into operational lifetime. Webb needs small thruster firings periodically to maintain its position at L2 and to orient itself for observations. The fuel for these station-keeping operations is the primary consumable that limits the mission. Design specification: 10 years minimum. Fuel budget after the exceptional launch. Estimates suggest 20 years or more of station-keeping capability. This means Webb, barring any hardware failure, may be operational through the 2040s. That is a decade of observational time beyond the minimum design requirement. The scientific implications are enormous. The programs that could not be completed in 10 years, the statistical surveys of large areas of sky, the long time baseline monitoring programs, the atmospheric characterization of many planetary systems, all become achievable within the extended mission. The early galaxy problem, which requires large statistical samples to resolve definitively, benefits directly from this extended lifetime. More years of observation mean larger survey areas, more spectroscopic confirmations, better statistical characterization of the luminosity function at high redshifts. The exceptional launch accuracy of a rocket that had been through decades of development was in some ways the most consequential event in Webb's mission, more consequential than any individual scientific result, because it determined the total amount of science the mission could produce. Let us now talk about the specific way Webb's discovery of early massive galaxies connects to the question of where we come from, about the chemical history of the universe, and why getting galaxy formation right matters for understanding our own origins. Every atom of carbon in your body was fused inside a star. Every atom of oxygen you are breathing was made in a stellar core or in a supernova explosion. Every atom of iron in your blood was synthesized in the last seconds of a massive star's life as it collapsed into a neutron star or black hole. These atoms were made in stars and then scattered into the interstellar medium by stellar winds and supernova explosions. They cycled through molecular clouds, through new generations of star formation, accumulating in concentration over billions of years. Eventually, in a cloud that had been enriched by many stellar generations, the Sun formed. And around it, from the rocky material left over after the Sun's formation, the Earth. The timing of this process matters. When in the universe's history were the first heavy elements available in significant concentrations? When did the interstellar medium become sufficiently enriched for rocky planets to form? When did the conditions for water-based chemistry, and ultimately for life as we understand it, first exist? The answers depend on galaxy formation history. If galaxies formed earlier and more massively than our models suggest, which is what Webb appears to be telling us, then the chemical enrichment of the universe happened faster. The heavy elements appeared sooner. Rocky planets may have been possible earlier in cosmic history than we thought. The specific timescale matters because it affects the question of whether we are early in the history of life in the universe or late. If the universe was already producing heavy elements and rocky planets a billion years earlier than our models suggest, then civilizations a billion years more technologically advanced than ours
are not just theoretically possible, they had more time to develop. This is speculative. We know nothing about life beyond Earth. But the background conditions set by galaxy formation history are the foundation on which any speculation about the prevalence and age distribution of life in the universe must be built. Getting galaxy formation right is not only a problem in astrophysics, it is a foundational question for understanding the context in which life is or is not common. Let us now talk about a specific observational program that Webb is conducting that has nothing to do with distant galaxies, about its observations of solar system objects and what these reveal about our immediate cosmic neighborhood. Webb has observed Jupiter, Saturn, Uranus, Neptune, and their moons. These observations are not the primary scientific driver of the mission. They were included in the science program to demonstrate Webb's versatility and to address specific questions that require infrared sensitivity. The Jupiter observations produced some of the most striking images from the mission's first year, showing auroral emissions, the Great Red Spot, the faint ring system, and several moons simultaneously in the same field. The infrared view reveals atmospheric structure at different altitudes that is invisible in visible light. Of greatest scientific interest, Webb observations of Titan, Saturn's largest moon, contributed to studies of Titan's atmospheric chemistry. The thick nitrogen atmosphere, with its complex organic photochemistry, is detectable and characterizable by Webb's instruments in ways relevant to understanding similar processes in the atmospheres of exoplanets. The Neptune observations showed the planet's ring system with clarity not achieved since Voyager 2 flew past in 1989. Webb's infrared view revealed details of the ring structure and the atmospheric temperature distribution. The Mars observations provided thermal emission data from the planet's surface and atmosphere that supplement the in situ measurements of rovers and landers. Most notably for astrobiology, Webb observations of the outer solar system are building a baseline understanding of the infrared spectral properties of icy bodies, organic-rich bodies, and atmospheres with diverse chemistries. This baseline is directly applicable to interpreting spectra of exoplanets, understanding what different types of chemistry look like in infrared spectra. Everything Webb learns from observing Titan's atmosphere, Ganymede's icy surface, or the organic compounds in comets contributes to the spectral library that will eventually be used to interpret the atmospheres of distant rocky planets that might harbor life. Let us now talk about the specific way Webb's observations fit into the historical progression of deep field imaging, about how we went from the Hubble Deep Field to where we are now. The Hubble Deep Field, released in January 1996, was a transformative image. 10 days of observation, an area of sky smaller than a dime held at 75 feet, about 3,000 galaxies. The reaction was immediate and profound. Scientists had debated how many galaxies existed in the observable universe. The Hubble Deep Field answered, far more than anyone expected. Galaxies were everywhere, in every direction, at every distance. The Hubble Ultra Deep Field, 2004, went deeper. About 10,000 galaxies in a slightly larger area. The faintest objects at the edge of Hubble's sensitivity were the earliest galaxies Hubble could see. The Hubble Extreme Deep Field, 2012, accumulated from 10 years of Hubble observations, reached about 5,500 galaxies, and pushed Hubble to its absolute limit. Webb's first deep field, SMAC SO723, was produced in approximately 12 hours of observation and showed comparable numbers of galaxies to the Hubble Ultra Deep Field, but at much greater depth in the infrared. In that first 12-hour observation, Webb surpassed what Hubble achieved in its deepest multi-year programs. This is not an incremental improvement. It is a categorical shift in capability. Webb's first 12 hours of deep field observation exceeded Hubble's best multi-year programs in infrared depth. What Hubble could not do in a decade of dedicated observing, Webb can surpass in a day. This capability difference directly enabled the discovery of the early massive galaxy problem. These galaxies existed at redshifts where Hubble could barely detect them as single pixels. Webb resolves them, measures their luminosities accurately, and obtains spectra that confirm their distances. The progression from Hubble Deep Field to Webb Jade's Deep Field represents 27 years of technological development that produced an instrument fundamentally different in kind from what preceded it, not just better, but operating in a regime that was previously inaccessible. Let us now talk about the specific way that data from Webb is processed and made available, about the open science philosophy that governs the mission, and why this matters for the quality of results. All Webb data enters a standard pipeline that performs calibration, flat fielding, dark subtraction, cosmic ray rejection, and mosaicing. This pipeline is publicly developed and maintained by the Space Telescope Science Institute. Updates to the pipeline are released as understanding of the instrument improves. Observations go through a proprietary period, typically up to 12 months, during which only the observing team can access the data. After the proprietary period, all data is publicly available through the Mikulski Archive for Space Telescopes, MAST. However, a significant fraction of Webb's time is allocated to community programs that have 0 or short proprietary periods. The early release observations, ERO, including the first public images, had no proprietary period. The early release science, ERS, programs had minimal proprietary periods. These were specifically designed to put data in scientists' hands as quickly as possible. The result, within weeks of the first science data being collected, researchers worldwide were downloading it and producing results. The paper by Labbe and colleagues, identifying 6 massive early galaxies, was submitted to Nature 6 weeks after the data became public. Multiple other teams were independently analyzing the same data during that period. This open science approach, where the same data is simultaneously available to hundreds of research groups worldwide, creates an automatic cross-checking mechanism. If one team misinterprets something, the error is quickly identified by other teams seeing different results from the same data. Scientific results emerging from multiple independent analyses of the same data carry much more weight than results from a single team. The speed at which the early galaxy problem emerged, within months of first light, and the speed at which it was both reinforced and refined by multiple independent teams, is a direct consequence of this open data philosophy. Let us now talk about something that connects the very first moments of the universe to the specific galaxies Webb is finding, about inflation and what it tells us about why structure exists at all. Before the Big Bang, or more precisely, in the earliest moments we can theoretically describe, the universe underwent a period of extraordinarily rapid exponential expansion called inflation. In a tiny fraction of a second, approximately 10 to the power of minus 36 to 10 to the power of minus 32 seconds after the initial singularity, the universe expanded by a factor of perhaps 10 to the 26th power or more. Inflation solves several problems with the basic Big Bang picture: why the universe is so uniform in temperature, why it is so spatially flat, why certain artifacts predicted by pre-inflation physics are not observed. But inflation also provides the seeds of all cosmic structure. During inflation, quantum fluctuations in the inflaton field, the field that drives inflation, were stretched by the rapid expansion from quantum to cosmological scales. These fluctuations became the tiny overdensities and underdensities imprinted in the early universe. These are the fluctuations recorded in the CMB. These are the seeds from which all galaxies grew. The specific statistical properties of these fluctuations, their amplitude, their scale dependence, their deviations from perfect Gaussianity, are predictions of specific inflationary models. Different models of inflation make different predictions. The CMB measurements confirm that the fluctuations are nearly scale invariant, the same amplitude on all scales, nearly Gaussian, following a specific random statistical distribution, and have a specific amplitude of about 1 part in 100,000. Standard lambda CDM takes these measured inflationary initial conditions and predicts how structures grew from them. The prediction is hierarchical galaxy formation, small structures first, large structures later. The fact that this prediction appears to fail at the highest redshifts Webb is observing raises a specific question. Are the initial conditions exactly what standard inflation predicts? Or is there some additional feature of the primordial power spectrum, some enhancement of fluctuation power at specific scales that seeded more massive structures earlier than standard inflation allows? This is one of the most exotic possibilities raised by Webb's observations. It would mean that inflation itself, the best model we have for the very first moments of the universe, needs modification. Not abandonment, the basic framework of inflation is well supported, but modification, an additional feature in the inflationary power spectrum. This is not the most likely explanation. Modified star formation efficiency in early galaxies is more likely. But the possibility that Webb's observations are pointing us toward new physics in inflation, the physics of the earliest moments we can theoretically describe, is why some theorists find this problem deeply exciting. Let us now talk about the specific scientific legacy that Webb is building, about what the archive of Webb data will mean for astronomy for the next century. Webb's data will not be analysed only by the researchers who collect it. The archive being built at MAST will be accessible to astronomers for decades. Future researchers using future analysis techniques, machine learning algorithms not yet developed, theoretical frameworks not yet conceived, will extract information from Webb's data that its current analyzers cannot see. This is a pattern established by previous great observatories. The Sloan Digital Sky Survey, which imaged a quarter of the sky between 1998 and 2009, continues to produce scientific results today, decades after its initial operation, because its data continues to be mined with new techniques. The number of scientific papers per year based on SDSS data has not declined with time. It has increased as more scientists have learned to use the archive. Webb's data archive is more complex, richer in information per source, and covers wavelength ranges inaccessible to any previous survey. It is reasonable to expect that Webb's archive will be a primary resource for astronomical research well into the 22nd century. The early galaxy problem that Webb has raised will be one topic that future generations of astronomers return to repeatedly. As theoretical models improve, as new observational data provides additional constraints, as complementary observations from ELT and other facilities add detail. But the archive will be relevant to questions we cannot currently anticipate. Questions about topics that have not yet been identified as important. Questions generated by theoretical developments that have not yet occurred. This is the nature of a great observatory. Its scientific legacy extends far beyond the careers of the people who built it, operated it, and first analyzed its data. Let us now talk about the most concrete connection to tonight's sky, about what you can observe with your eyes and with simple instruments that connects to what Webb is doing. Saturn is visible from Earth for roughly 10 months of every year. Through even a small telescope, 60 to 80 millimeters of aperture at 50 times magnification, Saturn's rings are unmistakably clear. The disk of Titan, Saturn's largest moon, is detectable as a faint star-like point near the planet. Webb has observed the Titan system. Its infrared spectra of Titan's atmosphere have contributed to understanding the same photochemical processes that Webb's instruments detect in the atmospheres of distant exoplanets. Jupiter, even brighter and more prominent than Saturn, shows 4 Galilean moons through binoculars in good conditions. These moons were first observed by Galileo in 1610,
and were the first direct evidence that not everything in the solar system orbited Earth. Webb has observed Jupiter and its moons, including Europa, which hosts a subsurface liquid water ocean and is considered one of the most promising places to search for life in the solar system. From Jupiter to the most distant galaxy in Webb's field, from a few 100 million kilometers to 13.5 billion light years, is a span of about 10 to the 23rd power in distance, 40 trillion times the distance to Jupiter. In that entire range, Webb has contributed observations. Understanding the nearby informs the distant. Understanding the distant informs what is possible nearby. The sky above you tonight is not a backdrop, it is a volume. And in that volume, in every direction, at every distance, Webb is finding something worth knowing. Look up. Everything above you is part of the story, and the story is more interesting than we thought. Let us talk about something that is rarely discussed in the context of Webb's discoveries, about the specific human infrastructure that makes the telescope work, and what it means to operate the most complex scientific instrument ever built. The James Webb Space Telescope is operated from the Space Telescope Science Institute, STSCI, on the campus of Johns Hopkins University in Baltimore, Maryland. The Mission Operations Center is staffed around the clock 365 days a year. Operators monitor the spacecraft's health and safety, execute observation schedules, manage communications through NASA's Deep Space Network, and respond to any anomalies. Communicating with Webb involves the Deep Space Network's large antenna dishes, the same network that communicates with Voyager 1, with Mars rovers, with every spacecraft in the outer solar system. Webb is at L2, 1.5 million kilometers away, far enough that radio signals take about 5 seconds to travel each way. This is close enough for effective real-time monitoring of spacecraft health. The science scheduling is handled by a separate team using sophisticated software that optimizes observation sequences, fitting together the thousands of individual science programs approved for Webb's time into an efficient schedule that respects pointing constraints. Some targets are only observable at certain times of year. Thermal management requirements. Large sloughs between very different pointing directions change the telescope's thermal environment. And data volume management. The amount of data Webb generates must be manageable through the communications link. Webb generates approximately 57 gigabytes of data per day. This data is stored on board and downlinked to Earth during communication passes with the Deep Space Network. The data rate is not high by modern standards. A contemporary smartphone can transfer data faster. But the volume is sufficient for the science programs planned. Every photon that Webb's detectors is the result of this entire operational infrastructure working correctly. The pointing must be accurate to within a fraction of an arcsecond. The guide stars must be correctly identified and tracked. The thermal control must maintain detector temperatures within tight tolerances. The scheduling must ensure that the right instrument is configured with the right settings for the right target at the right time. When you see a Webb image of a galaxy 13 billion light years away, you are seeing the product of a chain that extends from the quantum mechanics of photon detection through the engineering of detector arrays, optical alignment, thermal management, communication links, pipeline software, and the dedicated work of hundreds of people who show up every day to operate a machine in space. The science is not separable from this infrastructure. The infrastructure is the science. Let us now talk about a specific and underappreciated aspect of Webb's scientific contribution, about what the telescope is revealing about the Milky Way's own formation history through a completely unexpected observational approach. The Milky Way is surrounded by a system of dwarf satellite galaxies, small galaxies gravitationally bound to our own. The most prominent are the Large and Small Magellanic Clouds, visible from the southern hemisphere as detached patches of the Milky Way on clear nights. Many fainter satellite galaxies have been discovered by sky surveys over the past 2 decades, but the census is incomplete. Smaller and more distant satellites are below the detection threshold of previous surveys. Webb is discovering extremely faint dwarf satellite galaxies of the Milky Way and its immediate neighbours through a technique called ultra-deep imaging, staring at a small patch of sky for many hours and detecting the extremely faint surface brightness of very low-mass systems. These faint satellites matter for galaxy formation in a specific way. The standard lambda CDM model predicts a certain number of satellite galaxies around a Milky Way-sized host. Early versions of the model predicted far more satellites than were observed, the missing satellites problem. Modified dark matter models and baryonic physics, gas and stellar feedback driving dark matter out of small halos, were invoked to explain the discrepancy. The actual number of satellites, when surveys are complete enough to detect the faintest systems, constrains both dark matter properties and the efficiency of early star formation suppression in small halos. Webb's sensitivity allows detection of satellite galaxies too faint for previous surveys, completing the census and providing a cleaner test of these models. This is a very different kind of observation from looking at galaxies 13 billion light-years away, but it addresses complementary aspects of the same fundamental question. How does gravity, mediated by dark matter, shape the distribution and properties of luminous matter in the universe? The answer has to be consistent across all scales, from the earliest massive galaxies Webb finds at Z greater than 10 to the faintest satellite galaxies orbiting our own Milky Way today. If the models cannot simultaneously explain both extremes, the models need revision. Let us now talk about what is perhaps the most philosophically significant implication of Webb's early universe discoveries, about what they suggest regarding the Fermi paradox and the prevalence of life. The Fermi paradox, the question of why a universe apparently capable of producing intelligent life has not produced obvious evidence of other technological civilizations, is not directly addressed by Webb. Webb is not a SETI instrument. It is not looking for radio signals or laser pulses or megastructures. But Webb's discoveries are indirectly relevant to one of the key parameters in the Drake equation and related frameworks, the timescale on which Earth-like planets became possible. Rocky planets require heavy elements, carbon, oxygen, silicon, iron, and others. These elements are synthesized in stellar interiors and distributed by supernovae. The first generation of stars, population 3, were made of nearly pure hydrogen and helium. After they died, their ejecta enriched the surrounding gas. The second generation could form with some metals, and so on through multiple stellar generations. The time required to enrich the interstellar medium to the metallicity needed to form Earth-like rocky planets is a key constraint on when habitable worlds first became possible. If Webb is correct that galaxy formation was more efficient and happened earlier than our models suggest, then heavy element production also happened earlier. The interstellar medium reached Earth-compatible metallicities sooner. Rocky planets could form sooner. This means habitable worlds, in principle, could have existed 1 billion or more years earlier in cosmic history than our current models suggest, which means, if life arises with any reasonable probability on habitable worlds, technological civilizations could have had 1 billion additional years of development time beyond what we previously estimated. 1 billion years is not a trivial increment. It is longer than the age of multicellular life on Earth. It is longer than the time it took eyes to evolve, longer than the time it took intelligence to evolve. A civilization with a billion-year head start on us is not just more technologically advanced, it is likely unimaginably different in character from anything we can extrapolate from our own trajectory. Webb is not answering the Fermi paradox, but it is adjusting the background assumptions against which the paradox is evaluated. If habitable worlds existed earlier and in greater numbers than we thought, the Fermi paradox becomes more acute. The silence becomes more puzzling. Something must resolve it. Either life is rarer than we think, or civilizations do not persist, or they exist in ways we cannot detect. Webb's early galaxy discoveries are one more data point pushing this question toward the center of scientific attention.
Let us now talk about the specific way that Webb's discoveries connect to the question of dark matter in a concrete observational sense, about what early massive galaxies tell us about dark matter halo properties. In the Standard Model, the most massive dark matter halos at any given epoch have a maximum mass determined by the initial power spectrum of density fluctuations and the time elapsed since the Big Bang. This maximum halo mass, sometimes called the nonlinear mass scale, sets an upper limit on galaxy mass at each epoch. No galaxy can be more massive than the halo that hosts it, and halos cannot grow faster than the initial conditions and gravitational collapse physics allow. Webb's early massive galaxies are approaching or exceeding these mass limits. This is the specific technical meaning of too massive too early. The stellar masses imply host halos that should not yet be that massive. One possibility: the initial power spectrum of density fluctuations, set by inflation, had more power on small scales than the standard, nearly scale-invariant spectrum predicts. More power on small scales means more small halos form earlier, and rare massive halos can also assemble earlier from these abundant small building blocks. This modification to the primordial power spectrum is constrained by CMB measurements, which require it to be nearly scale invariant, but small deviations from perfect scale invariance are allowed. Some theorists have proposed specific modifications that are consistent with CMB data while providing more structure formation at high redshifts. Another possibility: dark matter is not perfectly cold. Warm dark matter, with a small but non-negligible thermal velocity, suppresses structure formation on small scales relative to cold dark matter.
This is the wrong direction for explaining massive early galaxies. Warm dark matter makes it harder to form structures, not easier. But more exotic dark matter models, self-interacting dark matter, ultralight axion dark matter, primordial black holes, can change the distribution of halo masses in complex ways. Some of these models might allow enhanced clustering of matter on the specific scales relevant to the massive early galaxies Webb is finding. The connection between Webb's early galaxy observations and dark matter physics is actively being explored. The galaxies Webb finds are the observational signature of the underlying dark matter distribution. Reading that distribution from the galaxy observations, even imperfectly, constrains what dark matter can be. Let us now talk about something that connects every observation Webb has made to the night sky above you, about the light that is arriving right now from every direction and what it represents. The light that enters your eyes when you look at the night sky is not all the same age. Light from the Moon, about 1.3 seconds old. It left the Moon's surface less than 2 seconds ago. Light from Venus at its closest, about 2.3 minutes old. Light from the Sun, about 8.3 minutes old. Light from Jupiter, about 35 to 52 minutes old, depending on the planet's positions. Light from Sirius, the brightest star in the night sky, about 8.6 years old. Light from Polaris, the North Star, about 433 years old.
It left Polaris in the 1590s, during the time of Galileo and Shakespeare. Light from the Andromeda Galaxy, visible as a faint smudge to the naked eye under dark skies, about 2.537 million years old. It left Andromeda when our ancestors were Homo habilis, early human ancestors who had not yet developed language. Light from the most distant object visible to the naked eye, arguably the quasar 3C273 in Virgo, visible with a very good amateur telescope, about 2.4 billion years old.
It left 3C273 when Earth was young, before complex animal life had evolved. Light from the most distant galaxies in Webb's deep fields, about 13.5 billion years old. It left when the universe was 300 million years old. No stars like our Sun existed, no rocky planets, no chemistry that could support life as we understand it. All of this light, spanning 13 orders of magnitude in age, is arriving simultaneously, right now, while you read this. Your eye is receiving photons of many different ages simultaneously, from many different epochs of cosmic history, all compressed into the single experience of looking at the night sky. Webb sorts this light by wavelength, by redshift, by apparent brightness. It extracts the faintest signal from the oldest light. It reads the chemical composition of early galaxies from the specific wavelengths their atoms absorb and emit. But the light is the same light whether it arrives at Webb's mirror or at your eye. The photons do not know whether they are being detected by a 6.5-meter mirror cooled to 37 Kelvin, or by the rods and cones of the human retina. When you look up at the night sky, you are participating in the same act as Webb, receiving light from the universe, being touched by photons that have been traveling for minutes or years or billions of years. The difference is only sensitivity. Webb sees what you cannot, but the act is the same. And what Webb sees, galaxies more massive and more numerous in the early universe than our models predicted, atmospheres of distant worlds containing chemistry we are only beginning to interpret, the faint infrared glow of the universe's history going back nearly to its beginning. All of that is encoded in the same darkness that you see when you look up on a clear night. The darkness is not empty, it is full of photons from the beginning of time, full of answers to questions we are only now learning to ask, full of puzzles like the early massive galaxy problem that tell us our understanding is incomplete and that the universe is more interesting than any model we have built to describe it. Webb is reading that darkness, right now, while you look up. Go outside tonight. Find the darkest part of your sky. Look up. What you see, the stars, the faint smear of the Milky Way if you are far enough from city lights, the darkness between everything, is not what it appears to be. It is not silence. It is not emptiness. It is full. Right now, while you stand there, photons are arriving at your eyes from every direction. From stars a few light years away, from stars thousands of light years away, from other galaxies millions of light years away. Light that has been traveling for minutes, for years, for hundreds of millions of years, all arriving simultaneously, all compressed into the single experience of looking up on a clear night. And deeper than any of that, deeper than the eye can reach, deeper than any previous instrument could reach, there is light that left its source 13.5 billion years ago. Light from galaxies that existed when the universe was 300 million years old, when the darkness was just ending, when the first stars were just beginning to burn. That light is real. It is arriving right now at the mirror of a telescope 1.5 million kilometers from where you are standing. And what that light is telling us,
What the James Webb Space Telescope has read from photons that have been traveling since before the Sun existed, since before Earth existed, since before life existed, is that something in our understanding is incomplete. The galaxies should not be there. Massive, structured, containing hundreds of billions of stars, existing 200, 300, 500 million years after the Big Bang, at a time when our best models of how the universe works say they should not yet have had time to form. And yet, there they are. Not one, not three, dozens, found in multiple independent surveys, confirmed by independent teams, spectroscopically verified at distances that place them in the earliest epoch of cosmic history we can directly observe. This does not mean everything we thought we knew is wrong. The Big Bang is one of the most rigorously confirmed theories in the history of science. The cosmic microwave background, that uniform glow of ancient light filling all of space at 2.7 Kelvin, is direct evidence of the hot, dense, early universe that the Big Bang describes. The abundance of hydrogen, helium, and lithium in the universe matches Big Bang nucleosynthesis predictions with extraordinary precision. The expansion of the universe is measured across billions of years of cosmic history and confirms the basic picture. None of this changes. What changes is the detail, the specifics of how quickly the first structures formed, how efficiently the first stars converted gas into light, what role the first supermassive black holes played, what the initial mass function of the first stellar generations looked like, whether dark matter halos assembled on the exact timescale the Standard Model predicts. These are not small questions dressed up as large ones, they are genuinely large questions. The answers will reshape our understanding of how everything we can see came to exist. And we are finding the answers now, in this decade.